Hello and welcome to yet another South Korean college scholastic ability test video. The problem that I am going to solve today is this. For functions fx defined as x squared minus 4x plus a and gx defined as the limit of 2 times absolute value of x minus b to the power of n plus 1 divided by absolute value of x minus b to the power of n plus 1 as n goes to infinity, let hx be fx times gx. For constants a and b that make hx continuous for all real numbers x, what is the value of a plus b? Now, this problem is not one of those extremely difficult killer level problems, but one thing I found interesting is that this is only the 6th problem of the math section, which consists of 30 problems in total. I mean, the difficult problems are usually worth 4 points, but this problem appears so early in the test that it only gives you 3 points. And it is likely that this particular problem was challenging enough to make many students flabbergasted when they were taking the test. So how do we deal with this? Well, obviously, we have to deal with the most complicated looking one first, which is function gx. Upon close inspection, you'll notice that gx involves the limit of the geometric progression, which is this absolute value of x minus b to the nth power part. And this is the moment to find out whether the students have studied the limit of a geometric progression well or poorly. For a general geometric progression a to the power of n with common ratio a, its limit is usually dealt by dividing into 4 cases. If absolute value of a is greater than 1, then the limit of a to the power of n diverges. If a is positive, then a to the power of n simply becomes infinitely larger, and if a is negative, a to the power of n oscillates between positive and negative values, while its absolute value becomes larger and larger. If a is exactly 1, then the limit of a to the power of n converges to 1. If absolute value of a is less than 1, then the limit of a to the power of n is 0, since the absolute value of a to the power of n becomes smaller and smaller. And the last case. Usually the case where a is exactly negative 1 is dealt separately in many problems. In this case, a to the power of n now oscillates between positive 1 and negative 1 without approaching to a single value, hence the limit also diverges in this case. In our problem, the common ratio, which is absolute value of x minus b, is always greater than or equal to 0. This means that we can rule out case 4 where the common ratio has the value of negative 1. So let's deal with remaining 3 cases. First case, absolute value of x minus b is greater than 1. This condition is equivalent to x minus b is greater than 1 or x minus b is less than negative 1, which is again equivalent to x is greater than b plus 1 or x is less than b minus 1. In this case, absolute value of x minus b to the power of n goes to infinity. Since we have this expression on the denominator and the numerator, the entire fraction approaches the ratio between coefficients of highest order of magnitude terms, in this case 2. You can explain this by dividing both numerator and denominator by absolute value of x minus b to the power of n, and use the fact that these constant divided by infinity terms approach 0. Next case, absolute value of x minus b is equal to 1. This is equivalent to x minus b is equal to plus minus 1. Hence, x is equal to b plus 1 or b minus 1. In this case, absolute value of x minus b to the nth power stays at 1. Hence gx equals just 2 times 1 plus 1 divided by 1 plus 1, which gives 3 over 2. And the final case, absolute value of x minus b is less than 1, which is equivalent to x minus b is greater than -1 and less than 1, which is equivalent to x is greater than b minus 1 and less than b plus 1. In this case, this part goes to 0. So we have 2 times 0 plus 1 divided by 0 plus 1, hence just 1. If we combine these results, the graph of gx looks as follows. It has value 2 when x is greater than b plus 1 or less than b minus 1, 1 when x is greater than b minus 1 and less than b plus 1, and it has value 3 over 2 when x is equal to either b plus 1 or b minus 1. Now we construct function hx by multiplying this gx with quadratic function fx, and we want the resulting function to be continuous for all real numbers x. Here, function fx is continuous for all real numbers x, so our only concern is the points where function gx is discontinuous, which are these 2 points at b minus 1 and b plus 1. The function fxgx must be continuous even at these 2 points, and the only way that is possible is when the value of function fx becomes 0 at these points. That is, both fb minus 1 and fb plus 1 must be 0. Since fx is a quadratic function with a leading coefficient of 1, we can write fx as x minus b minus 1 times x minus b plus 1. You can easily expand this to obtain x squared minus 2bx plus b squared minus 1. If we compare this with fx equals x squared minus 4x plus a, we have minus 2b equals minus 4 and b squared minus 1 equals a. And we can easily solve this to obtain b equals 2 and a equals 3. Hence a plus b equals 5. Therefore, the correct choice is choice 3. And that's all for today's video. Now, if you want to take a look at more CSAT problems that are early number but fairly difficult, please go check these videos, and also please give this video a thumbs up. Thank you for watching, and I will see you in another video.